Hi everyone. Today I will be discussing about the electronic thermal conductance suppression in lightly doped bilayer graphene measured via Johnson noise thermometry. Typically, we think of electronic transport through materials as being diffusive. Electrons and/or holes frequently make collisions with phonons or impurities that alter their trajectories, but they rarely collide with each other. This makes each particle take an independent random walk throughout the sample. This is the transport we typically consider in most metals, conventional semiconductors such as silicon, and dirty graphene. However, what happens if we can make our sample cleaner to remove impurity scattering, and we can lower the temperature enough to kill off phonon scattering, but not so low that we also kill off electron-electron scattering? We enter the hydrodynamic regime, where carrier-carrier scattering becomes the dominant collision and relaxation mechanism. The particles no longer follow independent random walks, but are now highly correlated and move as a collective fluid. There has in recent years been experimental evidence for this type of behavior in monolayer graphene, bilayer graphene, and WP2, just to name a few systems. There's other systems out there showing this type of behavior, waiting to be discovered. Measuring thermal conductivity is a powerful tool for studying hydrodynamics and strongly correlated electron systems. In conventional non-hydrodynamic materials, the thermal conductivity kappa follows the Wiedemann-Franz law, where the ratio of the thermal conductivity to temperature and electrical conductivity is a constant called the Lorentz number, which is expressed in terms of fundamental constants. If an electron system is found to violate this law, it is a candidate for hydrodynamic transport. Previously in our group, we measured the thermal conductivity of clean monolayer graphene at the charge neutrality point at 60 Kelvin. We found a 20-fold enhancement relative to the Wiedemann-Franz law. We can understand this by considering the effect of a thermal or potential gradient on electrons and holes. In a thermal gradient, the electrons and holes move together unimpeded, but in a potential gradient, they move in opposite directions and generate electron-hole friction. The lack of friction in the thermal transport sector gives us such a large enhancement. In contrast to graphene, WP2, a semi-metal with separate electron and hole pockets, has been shown to have a strongly suppressed thermal conductivity due to hydrodynamics below 20 Kelvin. We can understand this by considering that collisions between charge carriers of the same sign conserve momentum and thus electrical current, in distinction from the electron-hole friction in monolayer graphene. Thermal current is not conserved in collisions of the same carriers. In this work, I've measured the thermal conductivity of bilayer graphene. Bilayer graphene has a unique band structure with two parabolic bands touching at a single point and no band cap. This has an interesting consequence on the ratio of kinetic to potential energy, which determines how important interactions are. In monolayer graphene, this ratio is constant with respect to chemical potential, but in bilayer graphene, this ratio diverges as the chemical potential approaches the charge neutrality point. What this means is that near charge neutrality, the effects of Coulomb interactions between electrons are strongly enhanced because the kinetic energy is quenched. This is the schematic of my device. The bilayer graphene is encapsulated in top and bottom hexagonal boron nitride, and that is capped on both sides with graphite gates. A contact gate near the edge strongly dopes the region not covered by the top graphite. Here is an optical image of the device. How can we judge the cleanliness of the device? We examine resistance curves for various temperatures. As we lower the temperature, the peak at charge neutrality continues to get narrower. At each temperature, we can assign a density, called N0, that is characteristic of the width of the peak and represents the number of free charges at charge neutrality. For our entire measured temperature range above 5 Kelvin, the density decreases with decreasing temperature. This means the residual density consists of thermally excited electrons and holes rather than disorder-induced charge puddles. The temperature scale of disorder in the sample is below 5 Kelvin, and the disorder residual density is below 2.5 times 10 to the 10 per centimeter squared. In our measured temperature range, we are thus never limited by disorder. I will briefly discuss our measurement technique. To measure the temperature of the electrons, we measure their Johnson noise with a circuit similar to this simplified one shown here. The reactive matching circuit improves noise coupling between high-impedance devices and 50 ohm amplifier inputs. The Johnson noise is proportional to the temperature of the electrons in a resistor, and in a small piece of graphene, this makes our thermometer a mesoscopic probe of the electron temperature. It is important to mention that at low enough temperatures, weak electron-phonon scattering causes the electron temperature to decouple from the lattice phonon temperature, and thus we can heat the electrons independently from the lattice. How do we actually measure the thermal conductance? We use our so-called self-heating technique. We pass a current through our graphene device, creating uniform Joule heat. This heat diffuses via electronic diffusion to the contacts, which act as a boundary condition at the base temperature. The resulting temperature profile in the device channel is parabolic. Our noise thermometer measures the spatially average temperature rise in the channel, and the thermal conductance is the ratio of the Joule power to the temperature rise. In analyzing our data, we compute the Lorentz ratio and compare it to the Wiedemann-Franz law, where the Lorentz ratio is defined as 1. Here I present the results of my measurements. The top panel shows electrical conductivity versus density and temperature, and the bottom panel shows thermal conductivity normalized to the same units as electrical conductivity, but note that I am now plotting it on a log scale as it varies over many orders of magnitude. This is the raw data. We compute the Lorentz ratio via dividing the thermal conductivity by the electrical conductivity, and we get the following plot, which I am also showing on a log scale. Note that white indicates the Lorentz ratio is equal to 1, blue is larger than 1, and red is less than 1. I've indicated for each density the Fermi temperature. Above this temperature we have coexisting electrons in holes, and below we have a degenerate semiconductor. We will now examine this data more closely. We can identify 3 distinct regions where the Wiedemann-Franz law is violated. The first region shows an enhancement by a factor of 5 at charge neutrality and high temperature. This is somewhat similar to what is seen in monolayer graphene, except here there is no upper temperature cutoff. It's thus hard to attribute this increase to hydrodynamics. The best we can say is it is likely some combination of cooling to the phonon bath, bipolar diffusion, and hydrodynamics, but we don't know in what ratios. The second region shows a 25-fold suppression of the Lorentz ratio to 0.04. This is likely a result of hydrodynamic transport in bilayer graphene, as such a violation of the Wiedemann-Franz law can't be caused by bipolar diffusion or phonon cooling. More work is yet needed to confirm this suppression. In particular, at lower temperatures, when the transport becomes impurity dominated, the Lorentz ratio should restore back to 1. The third apparent violation is at low temperature and high density. We believe this is an artifact of the noise measurement that is somehow related to the device becoming ballistic. Most of the dissipation happens in the contacts, which are thermally anchored, thus we don't measure noise from the channel. We can compare our experimental results with some theoretical predictions made by Mohammad Zarenia et al. The theoretical calculations were made with a simplified ansatz to the Boltzmann equation, so they should be interpreted qualitatively rather than quantitatively. While the theory focuses on the enhancement rather than a suppression, experimentally we see a weak enhancement and a strong suppression, so that is why I have plotted the results on a log scale. If we look at the inside of the theoretical plot, we see we have rather good qualitative agreement for the suppression, at least before the ballistic type enhancement starts masking the true Lorentz ratio. It's unclear why our measured suppression is so much stronger than the enhancement. It's possible that the graphite gate is too close to the bilayer graphene at about 8 nanometers and creates some screening, and that a yet cleaner device would show a stronger enhancement. We are currently working on fabrication of more devices. I will now try to explain in an intuitive way why electron-electron scattering as the dominant source of collisions can cause such a strong suppression of the Lorentz ratio. Here I am plotting an equilibrium Fermi distribution of a parabolic band at non-zero temperature. The top plot shows occupied states in kx-ky space, and the bottom plot shows an energy momentum cut. I'm also plotting the Fermi function for the left and right sides. Now, to create an electrical current, I can add a uniform momentum shift like this to the entire Fermi sea. The effective chemical potential for right movers is higher than for left movers. Now, if we add electron-electron collisions into the picture, they must conserve the total momentum of the system, which is exactly proportional to the total electrical current, thus it must be conserved. Electron-electron collisions will not relax electrical current. Now, to create a thermal current, I need to make my right-moving electrons hotter and my left-moving electrons colder. The resulting distribution looks like this. The thermal current is to the right in the system. To zeroth order, ignoring thermoelectric effects, this thermal current has no net momentum, thus electron-electron collisions are able to redistribute the individual particle occupations to relax the thermal current while conserving total momentum. Of course, the presence of impurities or phonons will relax everything, but the important point here is that in hydrodynamics, electron-electron collisions are the dominant scattering mechanism, and they can relax thermal current but not electrical current. There are some effects not caused by electron-electron collisions that can suppress the Lorentz ratio. The first type is caused by inelastic phonon scattering, and the second is caused by thermal smearing of the Fermi surface. The first type occurs only when the temperature is much less than the Bloch-Grunstein temperature. In my data set here, I've indicated the Bloch-Grunstein temperature for each density with the green curve. This is a plot showing theoretical calculations for the Lorentz ratio in a non-interacting system. Below the Bloch-Grunstein temperature, there is a strong suppression of the Lorentz ratio. The degree of suppression depends on the relevance of impurity to inelastic phonon scattering. Our experimental data in a corresponding plot looks like this. The suppression begins far above the Bloch-Grunstein temperature, so we cannot attribute it to inelastic phonon scattering. The second type of suppression, caused by thermal smearing of the Fermi surface, occurs at temperatures above the Fermi temperature. The Lorentz ratio is 1 below this temperature and decreases to a constant value above it. This does not match our experimental suppression, and that cannot explain it either. I will now summarize and conclude my talk. Hydrodynamics can affect thermal transport and cause violations of the Wiedemann-Franz law. Bilayer graphene is a good candidate for hydrodynamics at or near charge neutrality. We measured the thermal conductance of bilayer graphene using Johnson noise thermometry and found a strong 25-fold suppression just away from charge neutrality, as well as a weak 5-fold violation at zero density. The suppression is likely caused by hydrodynamics, since electron-electron collisions conserve electrical current, but can relax thermal current. In future experiments, we will measure more devices at lower temperature and higher density. Finally, I would like to acknowledge the Philip Kim group as well as my two mentors Jonah Weissman and Jesse Krosno. Thank you for listening to my talk.